Awesome. Great. Well, welcome everybody to our March Early Career AGU Geodesy webinar. We're very glad to have our speaker today, Yao Yu, who is currently a postdoc at the University of California, San Diego. She received her bachelor and master's of engineering degrees in geodesy and geomatics from Wuhan University in China, and received her PhD at UCSD 2 years ago. Currently, she is a Schmidt AI postdoc working with David Sandwell, focused on understanding ocean seafloor interactions, deep ocean mixing, and regional ocean circulation over seamounts. So we're going to hear from Dr. Yu for about 45 minutes, and then we'll take questions at the end. At the moment, I have everyone muted and the chat closed, but at the end of the talk, we'll let everybody participate. So take it away.
Thank you so much, Matt, and thank you for giving me this opportunity to present to the big geodesy community. So the work I'm going to talk about is Abyssal marine tectonics from the SWOT mission. I will first talk about the seafloor mapping and introduce the SWOT mission. Then we'll talk about the major findings of this paper. And in the end, talk about what we can do in the next steps. Okay, so seafloor mapping status. Currently, only 25% of the seafloor is mapped by ship sonar. And this is gold standard to map the seafloor by ship sonar. For example, the research vessels, they generally carry a multi-beam sonar and they can directly map the shape of the seafloor with a resolution about 100 to 200 meters. And on the left, we show the coverage of ship sonar using blue lines. And we can see in some regions like Japan, it's fully mapped. But in the Southern Ocean, there are a lot of empty areas because it's very hard to get there. But seafloor mapping is very important for societal needs and the scientific applications. For example, the submarine undersea navigation, the cable pipeline routing, ocean circulation, seafloor tectonic studies, and on tsunami propagation and ocean mixing. The issue is the seafloor mapping using ship sonar is very slow and expensive. For example, in the white box, I circled the MH370, the Malaysian airline, which got lost, the search area. On the right, it shows the multi-beam coverage. This area has been surveyed with joint countries' efforts for 2 years, but only covers less than 0.1% of the seafloor. Seafloor mapping is slow and expensive, and it will take roughly 200 ship years, one ship marrying the ocean nonstop for 200 years to map the remaining 75% of the seafloor. It's gonna cost $3 billion, not too expensive, like the Mars Curiosity mission cost $2.5 billion, but we still need to get permissions from multiple countries to survey the coastlines, the regions. It's more like a political problem. So for the remaining 3/4 of the ocean, we need to rely on indirect mapping from satellite altimetry. Since the 1992, people have been putting the effort to use the traditional NIDA satellite altimeter that send the echo beam that measure the shape of the sea surface, then derive the shape of the seafloor. NIDA here means down looking. And the bumps and dips of the mean state of the sea surface, they reflect the shape of the seafloor. For example, if there's a seamount, because the rock is denser than the water, it will have extra gravitational pull and will attract water to pile up. And roughly a 1 meter tall seamount gonna attract actual 1 meter tall bump in the mean sea surface. So it's pretty large signals. But the resolutions are only about 12 to 16 kilometers because it is upward continuation problem. And in recent years, we have a SWOT. SWOT is a wide swath radar interferometry mission, and it promises a moderate resolution of 8 kilometers of the seafloor or gravity field. From 12 or 16 to 8 kilometers, it's a huge jump. So here's the timeline of a modern radar altimetry mission. It started in 1992 with the launch of ELS-1. And over the year, there are multiple missions being launched. And the orange ones are those in operation. And out of all these missions, they are basic all the NIDA, like a one-dimensional profiling radar altimetry missions, except for SWOT. SWOT is a INSAR mission and also allows to measure the height of the ocean. So it has many advantages. For the traditional NADA set altimeters, it sends the radar pulse to the sea surface. So the radar pulse will form a footprint on the sea surface with roughly 10-kilometer radius. So basically everything within this 10 kilometers radius will be averaged and smoothed and be recorded at the height measurement. It measures in 1 dimensions, gives a result like 20 times per second, like with 20 hertz. And the spatial resolution of the traditional night altimeter is about 50 to 100 kilometers, mostly limited by the noise level, instrument noise level, and the cross-track direction, cross-track distance. So this is what we had before SWOT. And the key factors to construct the marine gravity field or the predictive bathymetry using the net altimeter relies on 3 things. The first is dense ground coverage, and we won't have many repeats to reduce the noise from ocean signals. For example, the A and B here, we show the ground coverage from the Geodesy 1 and 2. They are on the repeat tracks with the cross-track spacing of roughly 200 kilometers. And this more dense map shows the non-repeat tracks from CrossSat 2. It doesn't really repeat. Oh yeah, it's drifting and repeats for repeat at 369 days. So like these very thin lines from CrossSat 2 and the thicker ones, they are from the repeat tracks from Geosat, Altica, and Sentinel-3. So we need multi missions to have a dense coverage of the ground, and we want to repeat many times so we can reduce the ocean noise. And the second factor is a high accuracy. The Sarah Altica mission has a high accuracy, so it really contribute to reduce the noise level in the marine gravity map. The last one is diverse inclinations, because the net altimeter, they go in 1 dimensions, measure the along track sea surface height. And if we have missions coming from different inclinations, we can get more like east, west information. And the final marine gravity or predictive flow has 12 to 16 kilometers spatial resolution using 30 years of net altimetry data. And SWOT is really a game changer. The major conclusion from our research is like using 1 year of the SWOT ocean height data, we can make a better marine gravity field than we used to have using 30 years net altimeter. And I'll tell you why. So the SWOT, with the full name, Surface Water and Ocean Topography, it is designed to study the small-scale ocean currents and eddies and the global river systems. It measures the global water height in wide swaths. It had come with a left and right swath. Each swath is about 60 kilometers wide. It has a spatial resolution about 10 kilometers. And the orbit repeats every 21 days. The major instrument it carries is called Karen. It is Ka-band radar interferometry. It's on the both sides of the satellite with a 10-meter baseline. And the SWOT missions are operated by the French CNES and the NASA with the help from the Canada and UK. So the principle is that on both sides of the baseline, separate by with a 10-meter distance, like both of the antenna can send pulse to the sea surface and reflect it back. So the R1 and the R2, they're the travel distance because the satellite is very tall, like 900 meters above the sea surface. The R1 and the R2, they will be very similar, but with a tiny difference. So if we want to know the height of the sea surface edge with reference to an ellipsoid, we can use the interferograms or the fringes shown by the delta R. Basically, the Karen measures the phase difference, and there's a rough relationship between the height and the phase difference I provided here, and here it relies on several things. Those changes with time is like the capital H, the altitude from the satellite, which can be provided by the GPS on the satellite. And the look angle is pretty small, like a 1 to 4 degrees. So it's really designed to measure the height. And we'll have issues over large slope area with a lot of layovers. And I want to share something that is why SWOT is the only INSA instrument for radar altimetry, while all others they're neither looking. Because previously people didn't think SWOT gonna work. To make it work and measure the height with high precision. For example, SWOT performances reach 1 centimeter high precision. It requires to know the baseline really well, like the angle of the raw angle of the baseline up to 1 microradian. If it's a 10 meters long, which means we need to know the shift up to 0.01 millimeter, like the width of the hair. It is like impossible, but the JPL engineers made it work. So SWOT gonna be the future standards for radar altimetry missions. Okay, so the Karen instrument has multiple advantages over the traditional neither looking altimeter. First, because it is SWOT measurement, it provides data on 2x2 kilometer grids over the ocean. And previously, it's one-dimensional profile. For example, in the center of this plot, you can see a NIDA altimeter path. It also carries a NIDA instrument. But with a wide swath, it collects data 100 times more efficient. And because it has provides this swath measurement, you can get a data from like all directions along track and cross track. So it overcomes that diverse inclination problem. And third, the noise level of SWOT is 1 magnitude lower than NIDA altimetry. It provides much higher accuracy data. And so I really want to thank the JPL engineers to make it work amazing. So here's the overview of SWOT. It was launched in December 2022. Then it went to the commission phase. Then in April 2023, it was put on the on the 1-day orbit and in the calibration validation phase, where the satellite only go through certain locations, and the people can use this data set compared with like in situ measurement or other satellite missions to validate the SWOT result. And I put a dark blue box here. That is our validation site. Then in July 2023, it shifted to a science phase orbit, where it measures the global ocean as a 21-day period and covers the global ocean, but with some like diamond data gaps. And up to July 2024, it has collected 1 year of global data. So we use this 1 year time span to construct a marine gravity field, and still operating with a nominal time lifespan of 3 years, but we're optimistic about how long it can operate. So the ocean data, they're distributed on 2 by 2 kilometer regular grids, which means like in another 21 days, they will provide data on exactly long lat grids. It's very easy to operate. And they also provide the intervarograms and on small tide, 250-meter irregular grids. So if you want to reach a higher resolution, you need to go to the irregular grids. Oops. Oh, this is a movie. But anyway, I'm gonna move to the next page. So using the CalVal data, we evaluate the SWOT precision and the spatial resolution. We chose this foundation seamount area because this area has multiple advantages. First, it is fully covered by ship gravity and the bathymetry measurement. As in the left plot, the green polygons shows the coverage of ship measurements. They're showing these thin white lines. So we can construct a high resolution mean sea surface or mean sea surface slope by using the ship gravity. And the yellow polygons shows the SWOT 1-day repeat that comes with a ascending and descending track. So basically, we use if we want to evaluate the SWOT precision and spatial resolution, we need to have a ground truth. And we build this ground truth using the ship gravity and the bathymetry. Like we construct a very high resolution mean sea surface slope. It has a resolution about like 7 kilometers and 1 microradian precision. And we chose this area because it covers multiple seamounts and it's on the very young seafloor. So basically no sediment and it's just a rock with uniform cross density. And because it's young, it's roughly 208 meters to 350 meters deep. It is roughly 1 kilometer shallower than the mean ocean basin. So it has a better signal to noise ratio. And this area has a very low ocean dynamics, so less noise and large seamount. With this large signal to noise ratio area, we evaluate the performance of the SWOT. So on the right, this grayscale map, I'm showing the along track slope and cross track slope from the wind path of SWOT. Like these bumps, they correspond to the shape of the seamounts. They create pretty large signals, like up more than tens of microradians, just in a 1-day snapshot. So in this CalVal orbit, they have roughly 100 repeats. We stack these repeats, try to reduce the ocean noise, and compare with the model slope in the along track and cross track directions. Oh, I think here I'm showing the along track. And the conclusion is that the SWOT stack accuracy stack of roughly 60 or 90 repeats is about 1.2 microradian. 1 microradian, 1 centimeter height over a 10-kilometer horizontal distance. And the resolution, the spatial resolution is about 8 kilometers. That is, but we think the resolution is a conservative estimate because the ground truth we built has a spatial resolution of 7 kilometers. This is the stack result. Then we look at the accuracy and spatial resolution as a function number cycle used using the bootstrapping. And we put the 30 years transition altimeter performance at the dashed gray line. And the look shows after roughly 10 cycles or like 9 months, the SWOT already exceeds the performance of traditional red altimeter in constructing a marine gravity field. And now we have roughly 30 cycles, so the performance is even better. And ultimately, it will reach resolution roughly 2 times the ocean depth. Oh yeah, on the left we show the along track and cross track performance. Because in the cross track there's the biggest error is called roll error. Because we cannot estimate the roll angle of the baseline perfectly. That introduced the biggest error. So people are coming up with ways to reduce the error. But in theory, like the height measurement in the Y swaths, it should have uniform accuracy and spatial resolution across all directions. So here in this slide, I'm showing the comparison between the traditional net altimeter on the left and the SWOT on the right over the Gulf Stream. On the left is a combination of 7 missions. Each mission provides a profile. So they merge of them and create this grids. It has a resolution about 100 kilometers. But SWOT, just one instrument, provides this SWOT measurement with about 10-kilometer resolution. So they can really see the much smaller ocean dynamics. And for us, we can construct a better marine gravity field. So what signals are there in the sea surface height? On the left, I'm providing just a snapshot of the sea surface height being observed by SWOT over the foundation seamount area. And we can see the individual seamount as the positive or as a height anomalies. They create a bump, positive bump compared to the surrounding area. And this signal contains the geoid information. Geoid showed the non-uniform mass distribution of the Earth's interior of the solid Earth, and the mean dynamic topography, which shows the mean state of the ocean circulation, and the time varying part, which is the sea level anomaly, that is ocean dynamics. So for us, if we want to focus on the geoid to study the solid Earth, to study the seafloor, we need to extract the geoid information. So what we can do here is if we average multiple repeats, we can try to reduce the signature of a sea level anomaly, and then we can subtract the mean dynamic topography using a model, then get the geoid information. And we call geoid a potato. So this shows the shape of the Earth under ideal conditions when there's no winds and tides. And if it's fully covered by water, then the shape of the water will be exactly as the geoid, but we also have land. And so the Earth formed that its surface is normal to gravity, which is combination of the gravitational force and the Coriolis force. And we describe the geoid with reference to ellipsoid. So it shows the mass redistribution within the Earth, including the mantle and the core and the crust, and the geoid changes the time, showing the mass redistribution relevant to water. So for us, if we want to focus on the crust, the seafloor, what can we do? So first we collect the sea surface height data from SWOT, the global measurement, and we stack in time to reduce the signature of ocean dynamics. Then we remove the mean state of ocean circulation, the mean dynamic topography, to get a geoid. It has roughly 10-kilometer resolution. Then to extract the seafloor information, we rely on the seafloor has a shorter wavelength signals compared to the mantle and core. And the Earth's gravitational potential field is conservative, like its Laplacian is 0. And if we want to focus on the short wavelength signals, we can take the gradient. Whenever we take a gradient, we highlight the shorter wavelength signals. So for this work, we are looking at the vertical gravity gradient, which is the second order gradient in the vertical direction of the geopotential. So to really highlight the seafloor and get rid of the signatures of the other components of the solid Earth. what we do it here is like, because if we want to look at the vertical graphic gradient, VGG, we can use the height gradient over the in the horizontal, and it's circled in this red box. But basically, it's like the geoid height and the geopotential is connected by the Bronze formula, and by taking the second order gradient in the sea surface, we can construct the vertical graphic gradient in the vertical directions. So this is what we do. By taking the second order gradient, we can really highlight the seafloor signals. Like the GeoI showing the longer wavelength information, and the VGG shows the much shorter wavelength information, which is mostly the seafloor. So now I'm going to talk about the 3 findings using 1 year of SWOT data, including abyssal hills, small seamounts, and continental margins. Because we said the SWOT, it constructs a marine gravity map up to 8 kilometers in wavelengths. So its biggest improvement is really at the 8 kilometer wavelength band. And those are what we highlight in the paper. So first is abyssal hills. Abyssal hills, they're the most abundant landform on Earth. They cover 70% of the seafloor, and they show up at this elongated rayed shape. They're formed along the mid-ocean ridges by normal faulting and the magmatic processes. They're about a few kilometers wide, but much longer, and rising a few hundred meters above the surrounding area. So prior to SWOT, we could only see the rough relief of abyssal hills, but now we can see individual of them, and we can really characterize the width, height, length, and orientation. For example, here I'm showing the VGG of abyssal hills, like they're showing in positive VGG in red in the southeast Indian region, and they pave the space in between the fracture zones. And we highlight abyssal hill roughly 300 kilometers in length. And on the bottom left, we show a rotated abyssal hill. Abyssal hill, they have the same direction as the spreading ridge. So this rotated abyssal hills record a local magmatic event. So by modeling the abyssal hills, we can use it to refine the plate reconstruction models and study the local tectonic and magmatic history. And abyssal hills, uh, what I'm very interested in is that there are obstacles in ocean circulation. Like there are parallel hills, one after one after one. So when ocean currents and tides flow over, they will meet these obstacles all the time, and it's gonna convert the energy and create turbulence. So here are the abyssal hills at different spreading rates. From the left to right is from the ultra slow Southwest Indian region to the ultra fast East Pacific rise. At the slow spreading regions, the abyssal hill, they're short, wide, and tall. It's dominated by tectonic processes. But at the fast spreading regions, the abyssal hills, they have a much smaller relief, and it's narrower and longer, dominated by sturdy magmatic supply. Here I'm showing the comparison between the 1 year SWOT and the previous 30-year net altimeter result at this different location. This is the Southwest Indian Ridge. The signals is pretty big, so you don't see the biggest contrast. But when we move to the lower relief areas, and I'm highlighting a smaller area now in the SWOT, we can see much clearer structures and the delineations of abyssal hills, and some are only a few 1 or 2 kilometers in width. And we can see some of the tiny uncharted seamounts in the area as well. And the bigger contrast can be seen in the East Pacific rise because the signal there is so tiny. And now with a higher accuracy measurement from SWOT, we can really map individual abyssal health. And this is just from 1 year of data. Now we almost have 2 years of data, so we expect a clearer map. And the one interesting story about abyssal health is for the past 10 decades, past 10 years, people are debating whether abyssal health record the past sea level influenced by the past sea level change relevant to the glacier age or Milankovitch cycle. Generally, abyssal health, they're modeled as aperiodic or random process. But people are starting to notice the periodicities in abyssal health patterns and understand what introduced these periodicities. Is it relevant to the sea level change or not? It's a debate going on, but now with our marine gravity map, we can model the characterize global abyssal health and help to answer this question. The second example on the show is seamounts. Seamounts circle stern rods of the oceans, obstacles to the ocean circulation. And they're mostly extinct volcanoes. Rising can be a few hundred to several kilometers tall from the abyssal basin. And the number of seamounts and the height follow this logarithm relation. And in the current cut log, we have 43,000 seamounts. Most of them more than 1 kilometer tall. And we expect another 50,000 seamounts taller than 1 kilometer to be found. And SWOT has ability to tell us where they are. So in this map, I'm showing the East Pacific rise, where these areas are fully covered by ship soundings. On the left, we show the bathymetry from ship soundings, and it shows the big and the smaller seamounts. Like the biggest one is about 2 kilometers tall. And on the right, I'm showing the VGG from SWOT. So the seamount, they show up as a positive VGG. And for this biggest one, you can even see the flexure bending in negative VGG. So SWOT can tell us where are the seamounts, but it's a real potential is in finding the smallest ones. So we highlight a smaller area and label the several seamounts, and we compare on the bottom panel, we compare the bathymetry and the VGG, and we can readily identify 3 seamounts here. The smallest is about 450 meters tall, and for some others, it's hard to differentiate them from the signature of abyssal health or the background orange pure noise. So our conclusion is at a roughly 3.5 kilometer deep abyssal basin, we can identify seamounts roughly 500 meters in height. That is about 4 kilometers in diameter, can be seen by SWOT. So we are counting the seamounts, and we expect to find a lot more. And here I'm showing the seamount in the Cocos plates, circled in the magnifier. There are multiple smaller seamounts, and there's a big one, roughly 800 meters tall. And for the smaller ones, I don't know how tall they are because there's no ship sonar coverage, but they're a few meters tall. So, and they're newly identified by SWOT. And you can see in this plate, the distribution of seamount is very asymmetric. On one side, there's only a few, and on the other side, there are way more, and they kind of parallel to the fracture zones. So by studying the distribution of seamounts and small seamounts, it allows us to study the deeper processes, to study the tough spots and the mantle plumes. Oh, okay, I'm gonna skip this slide. And the last example is about continental margins. Continental margins, for example, the passive ones formed by sedimentation processes can be clearly seen in SWOT. Here is this example in the South American continental shelf. On the left, we show the flat continental shelf, and these structures are the faults and sediment layers. If you look at the bathymetry, it's gonna be flat because it's covered by sediments. But SWOT can penetrate through the sediments and show the tectonic structures. And in between the depth controls, this green, this blue linear structures, they're spring submarine canyons or ancient rivers. They were caved by the turbulent flows, and nowadays they bring the sediments from the land to the deep ocean basin and redistribute sediments and the nutrients. And SWOT now they show such clear structures of them, and they can reveal this structure buried under sediments. And I'm gonna show the example of ice. So this comparison shows what we have from 1 year SWOT and what we used to have from 30 years of net altimeter. And now we can see the submarine canyons in so much better details. And over the abyssal ocean, there's a much less noise. And I'm gonna show you more comparisons. This is at the Red Sea in the Antarctica, and this area is mostly ice covered. And in the 30-year net altimeter, it's way noisier. And south of the -66 is because the Jason satellite series couldn't go that far. And now with SWOT, we can see the structure so much better. Here we show we call it a fishbone or herringbone structure. It comes with an ancient ridge from the 150 million years ago. And on the north and south, it shows the fracture zones like the bones of the fish. And in between the fracture zones, we're starting to see the abyssal hills for the first time in history. And in the south, it shows the noise ice shelf and a few seamounts and even the structures of submarine canyons. Because the SWOT goes in the 77-degree inclination, so it has much dense coverage in the polar areas, can provide so much better map in the polar area. And this map will allow us to reconstruct plate in much better details and more accurately. And this comparison is at the Arctic archipelago in Canada. On the left, we show SWOT. It reveals the alternating positive, negative linear structures of VGG, which are typical of the rift zones where the basin was opening up. And on the right was from the 30-year net altimetry missions. And this area is surveyed by airplane. It provides gravity anomaly at 10 by 10 kilometer resolution, but our satellite measurement has a better resolution than airborne ones. And because this area is very shallow, if we accumulate more data sets and use a higher resolution product, it can reach a special resolution about like 1 or 2 kilometers, like much better than this one even. The take-home note from our study is that using 1 year of SWOT ocean data, we constructed a marine gravity map, which offers more detailed information than we used to have using 30 years of traditional net altimetry. And the biggest improvements, there are the roughly 8-kilometer wavelength band, including abyssal hills, small seamounts, and continental margins. And we update and release the gravity product on the Topex UCSD site. And now we are using this marine gravity map to make new bathymetry models. I want to use the remaining several minutes to talk about what's next, what we can do in the next steps. The first is we want to make some basic scientific products, including the seafloor map using SWOT marine gravity. So now, led by David Samuel, and with the collaborations with more than 30 people, we are predicting seafloor using the SWOT gravity map. There's a rigorous relationship between the gravity and the seafloor topography. So that is what we used to do for multiple decades. The issue here is like we don't know the cross density, so we need to make adjust between the parameters and the fitting in regional grids. But now with machine learning, we can skip this step, and it's actually performing really well in making a predict bathymetry. And we expect the optimal resolution, the seafloor, gonna be 2 times the seafloor depth. And there's a seminar on seafloor prediction given by David Samuel on April the 2nd. Here's the Zoom ID, and you can also contact me to get the Zoom link. And we're also making synthetic bathymetry models to include the abyssal hills and the new seamounts. So here, these 2 slides, I'm showing the old method, the old physics-based Nettleton method to predict the bathymetry. The gravity anomaly and the bathymetry, they are linearly correlated at a roughly 6 to 135 kilometer band. But the correlation coefficient, or like a scaling factor, is different for each grid. So we need to tune the parameters. But now with the machine learning, we use a distributed neural network. We can fit in the gravity anomaly and use the ship soundings as a label, and use 25% of the seafloor where there are ship soundings to train the model, and fit the global gravity anomaly and other components to predict the bathymetry. And it actually performs better than the old Nettleton method, and it's much easier to do so. The next project is led by Maria Seton to do the plate reconstruction. So with our SWOT marine gravity, especially the information provided by abyssal hills, they can make a much finer resolution crust map. The plate reconstruction relies on geomag peaks and the shape of fracture zones. They assume the plates, they are sliding on the fracture zones. And by using our map, they can fix some issues in the current Asian map and increase the resolution. I'm showing the Railroad Sea basin example, like on the right, we showed a herringbone structure, which is an ancient ridge, and the plates, they were propagating north-south. But in the crust age, they didn't have this ancient plate included, so it more likely to only use the another ridge information. So they're gonna fix this to make the age be symmetric across the herringbones. And the abyssal hill, they were where the seafloor is spreading. The seafloor spreading direction. So, and now we have the abyssal, we're gonna have the abyssal hill peaks covering 70% of the seafloor. So it's gonna really help to increase the spatial resolution of crust age. And the sciences using marine gravity we can do is to study the formation of abyssal hills. It is not pure random process, it has periodicities. And how is it formed? I'm showing example in the Southeast Indian Ridge, south of the Australia. I'm putting the white peaks that are abyssal hills on both sides of the spreading ridge. To me, it looks like they're symmetric. So what dominates is a formation. We don't know, but now we can try to understand this process. And SWOT offers much better pictures of microplates. And we can also study the submarine volcanism by monitoring the gravity change. We're gonna have 2 years of data. So in July this year, we're gonna release a VGG change on the TOPEX site, so people can use it to study the magma chamber. And SWOT as a SAR instrument, it can be used to study ice sheet melting as well. Because the major science objective is to study ocean dynamics and global river and lake systems, it has a small look angle. And the SWOT teams, they just mask out the ice sheet in the data set. But intergrams, they're beautiful. So if we do our own INSA processing, we can estimate the ice shelf height and the study estimate the ice sheet melting. It has many advantages over the like asset2 disinstrument because it provides wide swaths. So we did a case study of ice sheet basal melt rate over the Tuas Glacier. And the SWOT, they just offer these beautiful interferograms. Can show the amplitude and phase. If we do our own phase unwrapping and use orbit information to project phase, unwrap phase into topography. And we can see the structure of the sea ice and ice shelf. This comes with errors on some regions, and here's a big mountain here. It will have a layover issues, but over the relatively flat floating ice shelf, we can estimate the height change. So I think these are the exciting things we can do with SWOT. And of course, we can use it to study ocean dynamics and estimate the river height. That was the original science scope, but there's so much more we can do using SWOT data. Yeah, thank you so much for your attention.
Great. Thank you so much. I need to open up the chat and allow people to unmute themselves. And great. All right. That's a fantastic talk. Thank you so much.
Thank you, Matt.
First, I'll open up and see if anyone.
Oh,
Yes.
I'm afraid it's too technical, but I feel like the audience, they're Geodesy people.
I think it's going to be great. And so we'll see if anyone else has any questions. I will open it up, but I have a few questions myself. So, anyone online have a question they would like to ask, either in the chat or you can unmute yourselves now. Yes, Doug.
Not so much a question, but a comment. I'm a mid-ocean ridge and plate tectonic specialist, and I would say that it is not consensus of mid-ocean ridge people that the fast-spreading ridges have abyssal hills formed by magmatic processes. The main point of evidence there is if they form close to the axis, they get buried by lava flows, and the main growth of abyssal hills is in the neighborhood of 5, 10, maybe 15 kilometers off axis, whereas the formation of the crust is limited to maybe 3 kilometers off axis. So at the slow spreading ridges, the abyssal hills are very large and they're all inward facing faults, and it makes good sense for them to be formed by the tension of plates pulling apart and resolving as normal fault shear. Whereas at the faster spreading ridges, I think, well, certainly my favorite idea is that the abyssal hills are caused by flexure from the loading of lava flows in the inner 2 or 3 kilometers, and you get a mix of inward facing and outward facing faults basically as a flexure creates a graben. So I would not call that a magmatic process, just a subtle variation of differences in tectonic processes between fast and slow.
So it won't call it magmatic process, but more like a lava flow rather than to lava flow supply.
Yeah, it was sort of a bending process. You start out the seafloor flat, and if my watch side is the axis where there's loading from new lava flows, it bends this way, and you get a little tiny graben, resulting much more from the flexure than the extension. So
Yeah, thank you so much. Yeah, I'm learning these processes, and yeah, I appreciate your comments. Yeah, do you have any ideas on the like a periodicities or possible like a symmetric pattern of abyssal hills?
well, a few months ago I took a quick glance at I was at the leaf paper on the lower right there, and the periodicity seems to be most visible when you look at a very small number of profiles. And when you look at lots of profiles together, the periodicity is much less obvious. And so certainly very few people believe the correlation between Milankovitch cycles and abyssal hill frequencies.
Yeah, I personally I don't believe it, but we do notice some patterns in the abyssal hills. So, but needs to come with a different explanation.
Yeah, so I mean, certainly, yeah, that there can be reasonable periodicities, but they presumably vary with spreading rate. And uh,
Yeah, yeah. Thank you.
but yeah, so very impressive work. I'm glad to learn about how the satellite works. I've been
Yeah.
following David Sandwell's work on this for well since he started. So,
Yeah, thanks. It's just amazing because we have SAR instruments and the backscatter coefficient, they can show the, for example, internal tides in the 1970s, but it couldn't measure the height. And for many years, people didn't believe it's gonna work. But anyway, the SWOT demonstrated it's like it can really measure the height using the INSA instrument. It's amazing.
yeah, so I'm a little unclear still on the differences between a cross-track signal and a long-track signal. The long track is a little harder for me to follow. Uh,
Oh, let me see
but I
which
don't think I
page
need
it
to
is.
know. Uh,
Okay, yeah. So it's like we have a cross-track error that we need to address. But after fixing it, like the performance in all directions should be like the same, be uniform.
okay.
Yeah.
Great. Thank you, Doug.
Hmm.
Comment in the chat, just congratulating you on a great talk and a great resource for people to be able to download from Karen. But a question for you I have, is I think you talked a lot about stacking data together. And I guess my question is, have you seen really any evidence of some sort of changes in the VGG that you could think could be related to Earth processes? I'm thinking in particular of submarine volcanoes. Great paper out on doing that at Hunga Tonga, but I don't know if you could see sort of smaller scale eruptions in that.
Oh, we think so. I don't know if you saw the paper by Alan the Marvel AGU Sciences, AGU Advances last
Okay,
year.
I haven't seen that one yet, but I guess they were using
Um,
SWOT to detect some eruptions.
they used the old VGG map to detect the eruption. No, to estimate the magma chamber, like the volume. But they give some estimates of SWOT potential. So she contact me. I'm gonna provide the VGG change in July because we wanna have 2 years of data and the 1 year subtract the other year to estimate the magma flow. Because the most signals gonna come from the ocean, like ocean eddies. Let me see if I have I skipped that page. Most signals will come from the ocean eddies, like this one. Um, but with other things like ocean color map, we can try to we can identify a few. Maybe it's do some case studies and to see if we can estimate the magma chamber change through VGG. But I have no idea like how big it has to be detected by SWOT. But the ocean dynamics is gonna be the biggest challenge here.
Great. I guess related question is, I guess what can you do, if anything, about waves? I mean, are they, does that count as part of your dynamic ocean correction? Are you sort of just averaging those out during the stacking procedure? How do you think? I mean, you had a good sort of isolation of all the different terms, but I wasn't sure if that was just sort of in the noise or if that was actually a useful signal that you can use as well, is sort of measuring wave heights.
That is a very good question. Very good. I was gonna put the noise map, but I forgot. Sorry.
No
So
problem.
SWOT, it's amazing. You can see the swells, internal tides, solitons, all these type of waves. It's been kind of like being averaged, so has reduced the height, but we can still see the signature. And for us, we do see a lot of solitons, like the nonlinear internal tides in multiple sites. Let me see if I can bring up this map, because I do want to show that. Okay, so I'm gonna stop share, then share again. I'm gonna share the whole screen. Could you see this gray map?
Yes.
Yes. So here's we like to look at grayscales, and this is the Mascarene Ridge, and this is a bank. Like there are two banks, and there's a shallow channel, and it's still loading. But you can see there are like waves propagating out. I hope it can focus soon. There are waves propagating out in both directions. There is the signatures of solitons because they have very short wavelengths, roughly 10 kilometers. So that is the biggest noise in our map. And there are people studying them in a SWOT measurement. So this is to track the solitons and the internal tides. It's a very important topic going on with SWOT, and there will be a nature paper on it coming out soon. I don't know which day, but I know the paper got accepted. Yeah, and for the large scale waves, and people they're doing tidal modeling to try to improve the tidal models around the coastlines. But these are not issues for us. The surface waves as well, they're also not issues because they're pretty small wavelengths. The biggest issue for us is soliton, like internal tides. But we are hoping to like average many years of data to reduce the signature.
Very cool. I'll be on the lookout for that paper. One final question I had for you was, I think the results you showed in the Arctic and the Antarctic were really interesting. Do I understand that basically you are only looking at those areas during the ice-free times of year, or are those areas where there's not a lot of sea ice? So I guess I'm just wondering if, like, you say it's a 1-year average, but in those particular areas, it's probably a little less. Is that true?
Super good question, Matt. Yes, we use the same 1 year data, but the right way to do it is to separate the local summer and winter data, and only use the summer data, local summer data to make the gravity. So it's less influenced by ice. You're correct. I did a really rough work. I can even show you the, wait, let me see if we can see the noise. Like you can see could you see the stripes? There's some bad data. I didn't add it. Like we just did a very quick work. But in the future, we'll need to separate the local winter and summer data for the polar area, and also use the 250-meter grids for the shallow regions and coastlines, because now we are using 2 by 2 kilometer data, which means the fundamental resolution will be restricted to be like 4 kilometers. But in some shallow water data, say like the water is only 500 meter deep, the resolution can be 1 kilometer. So we'll need to use the other higher resolution data set and merge them.
Cool.
I'll make a comment there that I looked at your grid that I downloaded a few months ago, and looking in the area northwest of the Ross Sea around the Balleny Islands, and I noticed several places where it was extremely noisy, like you had a few ice reflections that you hadn't taken out yet that made the older
I
grid look
did.
much better. I mean, obviously,
Okay, good.
it's a very useful first product, but I
Yes.
noticed it.
Oh, thank you so much. I didn't do edits.
So,
Um, yes, but could you let me know the region? Like
oh,
where is it?
sure. Yeah, let's see. Is your email on the science paper?
Yes. Let
Okay.
me put it here as well. Thank you so much. Because I'm how to say, I'm gonna prepare how to say process the 250-meter data now, and fix the issues. It's not fun. It's kind of like a challenging, but if I want to do it, I just want to fix relevant issues.
Yeah, so I would imagine either undergraduates or artificial intelligence could go through the polar oceans and say, "Oh, this looks much worse than the older grid." So
Oh, yeah, I
yeah,
think by separating like using more data flags and separating the winter and summer data, you will get better. Yeah.
yeah. Well, I'm sure it was. I find it much more valuable for you to release the data sooner, rather than spending a long time editing out some obvious problems. So I'm glad you released it sooner.
Thank you.
Great. Well, I think we will stop now. We've reached the hour mark, and we thank Dr. Yao, Dr. Yu again, sorry.
Thank
And
you, Matt.
thank you again so much for your great talk. And this recording will be available soon on the AGU site. So thanks everybody for coming again, and we'll see you later.